Hello, my structural analysis friends. In the last couple of videos, we spent talking about wind loads and the factors that affect their magnitudes. In this video, we're going to actually start doing some computations. I'll show you the equations and where you can find the factors that we're going to use according to ASCE 710. So without further ado, let's get started. So the ASCE 710 manual has several different methodologies for computing the effects of wind on structures. The one that we're going to be focusing on in our discussion today is called the MWFRS methodology, or the main wind force resisting system. And what this is the part of the structure that includes the columns and the beams almost exclusively. We're not looking at the effects of wind on the skin of the structure or on the on the partition walls of the structure on the outside of the building. Okay, the components or the cladding and those kind of things. Those are handled in other methodologies that may be covered in a later video, but for today, we're only looking at the main structural system itself, which is the columns, the beams, the girders, and so on and so forth. All right, so the methodology basically says that what we're going to calculate is we're going to calculate something called the dynamic pressure, okay? And the variable that the code uses is Q, and has a formula of something kind of like 0.00256 v squared. Okay, this is a dynamic equation, okay, that looks very similar to maybe Bernoulli's equation that you saw in a fluid mechanics class. All right, we've got a velocity squared kind of term. It's an energy based calculation. Okay, but what it does is it produces a dynamic wind pressure as a result of this. Okay, now what we want to be very careful of, and I'll warn you this up front, and then I'll show it as we start to kind of work our way through the process, is that the subscripts in this methodology mean a whole lot, everything, particularly when it comes to Q. Okay, so you're going to see things like QH and QZ in the manual and in these notes, so pay very, very special attention. Okay, QH is a very specific value. Okay, it's the measure of this calculation Q taken at the mean roof height of the building, and then QZ is that same calculation taken at any elevation in Z. Now I'm going to show you a basic diagram for our pressure as we start to kind of look at it. Okay, that will show how these loads affect, and you'll start to understand a little bit better how those things start to work. Okay, and that'll be coming up here in a page or two. Okay, so wind pressure then, this QZ at any value at any height, okay, and again, this is also QH when Z is equal to H, okay. It's basically the same basic formula. So you see here's the 0.00256, and there's the V squared, and then there's additional factors that come into play that kind of affect a bunch of different stuff. Now, we've talked about some of these. KD is our directionality. We talked about that in the last video. KZT is our topography. Again, talked about that in the last video. And then KZ is an elevation velocity pressure coefficient that we'll have to take a look at. Okay, and I'll show you where that comes from as well. So it's a very basic formula, very simple. Now, the things to note is on this is that V goes in miles per hour. Okay, and then once you do all of these calculations, what you get out is PSF. So this is a pounds per square foot calculation based on a miles per hour on V. Okay, so and the units adjustment has already been taken care of. I think that's kind of what's hidden in this 0.00256 partially. Okay, and so that's how we're going to handle that. All right. Okay, so let's talk a little bit about the velocity pressure coefficient. Okay, the velocity pressure coefficient is going to come out of this table 27.3.1. Okay, and you can see that it's set up fairly simply. The only information that's required to be able to figure this out is the exposure, B, C, or D, which one of those applies. And again, if you need some help remembering what those are, go back and look at the environmental effects video, and that will kind of explain the definitions of these. And then the only other thing you need to know is the elevation at which you're doing the calculation. So you can see that for very short structures, from 0 to 15 feet, it's a constant value. Wind is assumed to be constant, but as you start to go up in height, all the way up to this table goes to 500 feet, you can see that all of the factors start to increase as well. Okay, now this is, again, it's a variable pressure on what we call the windward wall, and as we start to kind of look at that. So let's see if we can pull up a sketch here. So the table is really easy. It's a matter of knowing your exposure and your elevation, and let's choose the coefficient that we need for KZ. Okay. All right. So here's what the wind pressure distribution is said to look like. Okay. So what I've done is I've drawn, for a flat roof building, something that kind of looks like this. Let's slide this over just a little bit. There we go. Okay. And so, get some of these smudges off of here a little bit. Live on the fly editing, right? Okay. All right. So here's our structure. And again, I don't worry about boundary conditions on this. It's just that it's got to be attached to the ground. And there's some terminology that is, so this is a cross section through the building, if you will. Okay. In our particular picture, or in this example, we're assuming that the wind is coming from the left and going to the right. Okay. The first wall that the wind hits is called the windward wall, and it takes the brunt of the force of the wind. Okay. The back wall on the opposite side from the windward wall is the leeward wall. Okay, now again, you could have columns in the middle of this. They don't affect anything in the distribution of the pressure to the surfaces. Okay, so we're going to abbreviate windward wall as WW. We're going to abbreviate leeward wall as LW. Okay, and then of course the roof is the roof. And again, the internal stuff we're not worried about at this point. Okay, what happens for a flat roof structure is the wind pressures look like the following. On the windward wall, the KZ value said from 0 to 15 feet, it was a constant pressure. So there's a constant portion here. Now, for most single-story buildings, your roof would be down here somewhere. It's pretty much a constant wind pressure assumed to be designed. Okay, but for taller structures, what we see is that the pressure starts to increase up here. Okay, so we're going to take that dynamic pressure calculation Q, and we're going to turn it into pressure P that we can now use to analyze our structure. Right, so you get this kind of trapezoidal shape on the upper portion of the building and then a constant over the first 15 feet. Okay, so the wind hits the building, and you can see that as you get higher up, it gets stronger and stronger. Okay, and then as the wind turns up the wall and then comes over the roof, it produces a kind of a high pressure uplift on the front portion of the wall. Okay, and so what will happen is that there will be dimensions that are set up for how much this distance will be. Okay. And generally speaking, it's on the neighborhood of about the height of the building, or the mean roof height of the building for this one. Okay, the next one then is a slightly lower pressure, and I call these zone 1 and zone 2 and zone 3 for the roof. So for about H from here to here, okay, it's about another H from here to here. Okay, and notice that that's the mean roof height that we talked about on there. Okay, and then anything beyond H gets a different smaller pressure. So it kind of, imagine it's coming up, it's swirling as it comes over the roof, and then it gets out toward the end of the building, and it starts to even out and move across the building at that point. Okay, once it gets to the back wall of the building, this leeward wall, okay, now it drops off, and we just assume that it makes a constant pressure on the back wall. So this is the picture that kind of tells our story, okay, for our structure. Recognize that this is the L dimension of the building. And remember, we said that L is in the direction parallel to the wind. So if we turn the wind on our building so that instead of being east to west, it's now west to east, this thing will flip-flop. Okay, and so then this trapezoidal region will be on the other wall. Okay, or if it turns and comes in from, say perpendicular to the page, something different will happen. So this is, in the plane that is parallel to the wind, what's the pressure profile that's happening. Okay, now, a couple of things to kind of point out on this, okay? Okay. The signs of the pressures are as follows, okay? So here's my windward wall, and again, I've taken the roof off just to kind of keep it clear, and then I got my leeward wall over here. But for the windward wall, okay, the pressure is pushing on the wall. It's pushing into it. This is considered to be a positive pressure, okay? It's a pushing type of pressure. Okay, whereas for the leeward wall, you'll notice that the arrows were pulling away from the wall. So this is producing a suction. Okay, and so in our definition for this methodology, suction is always negative. And as we saw up at the top, roof is also pulling on the surface, so that will be a negative pressure on the roof. Okay, so we got to kind of keep our signs straight so that our structure starts to work. So you can see that as the wind comes from, in this case, the wind is coming this way, that it's pushing on this wall, and it's also pulling on the back wall at the same time. So the total effect on the columns or the structure itself is an additive thing, that the windward wall and the leeward wall together are putting load in the same direction onto the structural members. But as far as applying to the structure itself, we have to watch the signs of these arrows to be very, very careful. Okay, now, if you look up at the top, the pressure at the top is taken as QH. So this is the Q taken at the roof elevation times G, which is a gust factor. I'll explain that in a second. And then the CP factors, which have to do with what wall is being acted on. Okay, so this is the windward wall CP, and then we have a leeward wall CP here. Okay, G is the same, and it's still QH as we start to kind of look at those. Okay, now, if you look at the lower elevations, on the leeward wall, it's QH again. So that subscript is just the same. So it's a constant pressure from here to here. Okay, whereas on the windward wall, the Q varies with the elevation. So what we have to do is we have to pick elevations to kind of help define the pressure. So normally what I do, since we know that this is 15 feet here, and I know that it's constant from here to here, I almost always choose a Z equal to 15 feet as a point of interest. And then with that, for fairly short structures, not super tall buildings, but 4, 5, 6 stories tall, I'm usually pretty comfortable taking a calculation from here and then doing one at the roof and just doing a straight line interpolation between the two. Okay, so really you only have to do a couple of QZ values. And in the exercises at the end of in the packets, if you're one of my students, you'll see that part of it. For everybody else, I'll show you the packet, kind of how we set those problems up as well. Okay, all right, so that will get us to that portion. All right, so pressure then, which is what we want, that's what we model for, is equal to this Q value times G times CP. Now again, whether it's a Z subscript or an H depends on the wall and depends on the loading that you're looking at. All right, so for the windward wall on here, the pressure is QZ, G, and then CP for the windward wall. That's what we told you. And then leeward wall is QH, G, CP for the leeward wall. And then for the side walls, we get kind of a different pressure as well. Okay, because in the ASCE code, okay, and we'll show you where these CP wall coefficients come from. What we've kind of drawn is a diagram that looks like this. This is an excerpt out of table 27.4.1 that kind of shows what the wind pressure is actually doing to a structure. So what we have here, and if I zoom this in maybe a little bit, I know it's a little blurry, but at least you can see the arrowheads on this point. Again, we're assuming that the wind is coming from the left. Okay, this is the windward wall, that's the leeward wall, but then the structure, now this is a plan view of it. Okay, so now instead of looking through the elevation of the building, we're now looking down on it. Okay, the side walls are then having a pressure that is, as the wind comes and turns around the side, because again, we're thinking in 3 dimensions here, that as the wind turns and comes around this corner, it starts to pull a suction force on the outside of the building. So again, this arrow is pulling on this wall, so if this is windward, this is leeward, that's side wall, and that's a side wall. You can see that it's pulling on this, so that's a negative pressure on that wall, and then it's pulling on this wall, it's a negative pressure on this one. Now, when you get into structural modeling, obviously, this may be a positive value, this may be a negative value in your model, but the minus signs that we get in this calculation indicate that the arrows are always pulling on the building. So it's up to you to be able to draw the picture for this. Okay, now for a gable or a hip roof, for a building that isn't a flat roof building, you can see that, okay, so now we're back to an elevation view. Here's my windward. Here's my leeward. And again, that's kind of that constant trapezoidal kind of thing. Okay, and then we have constant on the back wall, but the roof does something a little different when you start to get a pitch on the roof. You can see that there's a plus or minus sign depending on, different CP factors, and I'll show you that on the next table, that depending on how hard the wind hits the building and at what speed it hits it, I can get an effect that pushes the windward, this is called the windward roof here, can either cause the windward roof to push down or it can cause it to pull out, okay, depending on kind of the speed. And so we have to design for both of those cases, okay? And then the leeward roof, which would be this guy, is always a negative on those kind of things. All right, so that's kind of how we'll handle a gable or a hip roof. Okay? All right, now there are some minimum pressures. Okay, for walls, we don't reduce the wind pressure less than 16 psf, and for roofs, we don't reduce it less than 8. Okay, and so these will always be some minimums that kind of will be dealing. Now, for most of the problems we deal with, we won't get into cases that hit these minimums, but this is the minimum that has to be designed for, and that's a kind of one of those one-line statements in ASCE 710 27.4.7. It's easy to overlook that guy. Okay. Okay, all right, so let's talk about these CP factors. Okay, so CP, let's pull ourselves back out here a little bit so we can see things. This is probably the most confusing chart in the entire packet. We're looking at 27.4.1 again. Okay, and this is the table where our CP values come from. Okay, so for the walls, it's just this little bitty table happening here. Okay, I've got my windward wall, my leeward wall, and my side wall. Okay, so you can see for the windward wall, all values CP is a positive 0.8. So again, this has a positive value on it, implying that the wind is acting into the wall. Okay, and like I say, it's kind of hard to see, but you use that CP value with QZ, so they're telling you which Q. So this is the one that varies with height. Okay, for the side walls, also constant, and it's a minus 0.7 as a suction force. That's what that minus sign on the end. And you're going to use that with QH. Okay. The leeward wall, on the other hand, it depends on the building dimensions and how long the building gets and so forth and so on. So what we're going to look at is we're going to look at the L over B ratio on this. Okay, so remember, L is the direction parallel to the building. So if we're looking this way, then that is L and that is B. Okay, and so the L over B ratio, if it's between 0 and 1, your CP value is minus 0.5. If it's 2, it's minus 0.3, and if it's greater than 4, you're down to minus 0.2. So if you think about a value where L over B gets greater than 0 or greater than 4, you're looking at a very rectangular, long, narrow building to get to that greater than 4 value. And when you do that, it's a minus 0.2. Okay, now what do you do if you're in between these? You are allowed to interpolate in between these values if you want to. Normally what I do is I just tend to take just the larger of the two for that case. So if I'm at 1.5, I round it down to 1 and then we use minus 0.5. We'll get us there. Okay, so that one's pretty straightforward too. The one that's a little bit confusing has to do with the roof. Okay, and that's the lower table on this particular chart. Okay, so the way that we start to look at this and to understand what's going on is that for the first part up here, this is the gable roof. Okay, and this guy will be our flat roof. Okay, or in this case, parallel to the ridge. All right, so when we talk about the ridge of a building, if this is, if I draw this in kind of 3 dimensions here, this part right here is called the ridge. All right, and so now we got to figure out, if the wind comes in such that it's acting this way on the building, that's perpendicular to the ridge, whereas if it hits this end wall and comes down this way, it's parallel to the ridge. So depending on the wind dictates where you are and in which table that you're going to be. All right, so the first category, we call it the gable roof, okay? And this is normal to the ridge for gable roofs that are with a theta, and theta is the angle of the roof, that dimension. Okay, for theta greater than 10 degrees. Okay, so then just like you kind of did with the other one, we're going to take the H over L, and again, H is the mean roof height. That's this guy right here. Okay, and then L is the dimension that's parallel to the wind direction. So for H over L, you choose your value, you choose your angle, and then once you choose any one of these, so let's say that we were at 20 degrees and we had an H over L of 0.25, we would be over in this box here. You notice that one CP value is negative, one CP value is positive. That was that double arrow that I showed you back on the last page as we started to kind of look at that, if you remember. On the gable roof. Remember we had a suction force or a direct pressure force right here. That's the reflection of those two arrows. Okay, is one's positive, one's negative. And you have to analyze both cases. Now they don't occur simultaneously, so you have to consider them as separate load cases. So wind cases, you start to get lots and lots of different combinations that need to be analyzed. Okay, now the first part of this table, I didn't point this out right here, that's the windward wall. Okay, the last part of the table then would be for the leeward roof. Okay, and you see that for the leeward, the values are pretty constant for the different ranges. So that's how we handle, normal to the ridge for gable roofs. Okay, you can have normal to the ridge for flat roofs. You do it a little bit differently. Okay, and then parallel to the ridge for all theta. Okay, and so what happens is we look at our H over L ratios. Okay, and so for fairly long buildings compared to height, okay, we're up in these values, and this is kind of an interesting table, but this goes back to our sketch that we had of our pressure. All right, so what I'm going to do is I'm going to lay this down. Maybe if I can get both of them to show up. Okay, remember we talked about zone 1, zone 2, and zone 3 in this diagram. Okay, what happens if you look at the values that are happening for a distance from the windward edge or from the windward wall? So what we're doing on our picture is we're measuring from here, and we're measuring that way for a distance of whatever distance from this reference point. That's what measures the width of these pressures. Okay, now I called it as H, and then everything else, and you'll see why I did that as we start to look into this. All right, so horizontal distance from the windward edge for a flat roof from 0 to H over 2 has a minus 0.9 and a minus 0.18 as our CP factors. Okay, they're two different values, and you have to analyze both even though they have the same signs because they treat the building a little bit differently. Okay, but you'll notice that from H over 2 to H, I get the exact same values. So what happens is that this is kind of zone 1, this next guy is zone 2, and this guy here would be our zone 3 as we start to kind of look. So the minus 0.18 is kind of a flat constant pressure with no wind running. Okay, and so this would be minus 0.18 for all 4 of those ranges or all 3 of the zones. Okay, and this is kind of due to some like internal, mechanical equipment, air conditioning and stuff that apply a pressure inside of a building for a sealed structure that I can actually get kind of a balloon effect on the building. So this is kind of a minimum, no wind on the roof kind of thing, or the wind is hit hard enough and then dissipated out. That this would be kind of a minimum amount. Okay, but you'll notice then that I have minus 0.9 is zone 1, minus 0.5 is zone 2, and minus 0.3 is zone 3. And so that's how this is kind of laid out. So you got to kind of use these dimensions to kind of make the map of the roof. Okay, the map I showed you was for this case for a flat roof. Okay, now for cases where you start getting very tall buildings, you can see that it only goes from 0 to H over 2. Okay, and then from for greater than H over 2, it's a different set of values. Again, minus 0.18, and now we've got a minus 1.3 and a minus 0.7. Okay, right. So, and that will pretty much cover the majority of what I want to show you on this table. You can actually reduce the roof if you want to using these reduction factors. Okay, it says they can be reduced. So that's what this double star that you're seeing on this minus 1.3, that's a pretty big value on there. It's a pretty big, because you've got so much, the wind's coming up the roof, and then it turns that corner. It's got a lot of velocity and a lot of, suction pressure happening on the front end of the building. And that's what's happening on that. So that's how CP is determined. Okay. All right. So the basic methodology for how you would solve one of these. And I'll set this up just so you can kind of see the thought process of this. And this is one of the class exercises that my students will be working on here, is that we have a building, in this case, that is 200 feet tall. I know it's a little small. That's a 200. This is a 100. Okay, and then I've got my column grid lines for the perimeter of the building. Okay, it's 60 foot by 60 foot. And the goal is to be able to figure out what the wind pressures are that are acting on this. Okay, so the process that you go through when solving one of these problems then is that you're going to figure out what the risk category is, your importance factor, and your exposure category for the problem statement. So in this case, I gave that this building is an 8-story hotel on the Atlantic coast of North Carolina. Okay, maybe you're down in the Wilmington area, or or whatever the case may be. And so from this information, you can make some assumptions about these environmental factors. So again, if you need some review on this, go back and watch that environmental video. We'll walk you through how to determine risk category and importance and exposure as it pertains to wind. Okay, so that's the first step. The second step then is to start pulling off your factors that you need in order to be able to analyze the values of the wind. So the mean roof height, this is a flat roof building and it's 100 feet tall, so you would put 100 into this. Okay, the wind speed, remember, comes from the maps, and the wind speed map was a factor of the importance factor. Which category, exposure category, are we looking at for this? So that's why you needed these 3 before you could come down here. And so you can find your wind speed, and I have the exercise of trying to associate these labels with, what their variable name would be, and then the location of where that data came from. Okay, you got your topography factor, you got your directionality, Okay, and then once you have all of that, you can write this function as some form of Q equals some number times kz. So we haven't taken into account that elevation coefficient yet. Okay, so what we'll do is we'll use the next part of the table to be able to come up with what our kz values are. Okay, so this is our velocity pressure coefficient. So we'll do it at the ground elevation. So this goes at 0. The end of our uniform region, this is almost always 15. Okay, and then the end of the linear, this would be up at z equals to h. Okay, and then you basically look up the table for kz, what that kz value is. Okay, so that's why you would call this as kz. I'm basically working this part for you. Okay. All right, and then once you do that, then you can take kz and plug back into this equation. This is a qz equation at this point. Okay, and then you can do that computation here. And then at the end of the linear region, this guy here is basically your QH value when you do it. Okay? All right, which is what you would write in this line. So this is the process that we go through in order to be able to analyze this. It's really not that hard. Okay, so that gets you to the dynamic pressure, and then you can turn around and come up and calculate what the actual pressure is that is the loading on the building, the P pressure. All right, because remember, P is equal to Q, G, C sub P in our equation. So the Q's come out of this part up on step 3, and now I'm going to modify those values to come off of P. All right, now the gust factor for the 3-second gust, remember we talked about, is always 0.85 for what we're looking at. Okay, and then the CP comes from the table based on the wall that you're looking at, and then you get your Q, which is either QH or QZ. So that could be QH or QZ depending on what's required. Okay, and then this value is for the wall that you have. And so what I've done is I basically, when I do my pressure calculations, I break them up into the walls. I do a windward wall, and I fill out all this information. I do a leeward wall, and that's just a single value using QH. And that's what, again, why I'm asking for a reminder, which Q are you using? For leeward, it's QH. For sidewall, it's QH. This guy is QZ. Okay. All right. And so that will get you there. And then you go in and you kind of start playing with the sketch. Now, so what I've drawn is I've drawn kind of a plan view. Here's the windward, leeward, sidewall, and trying to come up with the plan view of what the pressure would look like. And that's just basically a reproduction of that graphic that I showed you for the plan view, that you have a windward pressure into the wall, sidewall out, and leeward wall out. Okay, now I have you doing this at the mean roof height, so you'll take the values at the top of the elevation diagram and be able to draw those like that. But you should be able to make this sketch. Understanding and visualizing what the wind is doing is very, very important. Okay, then you can go in and you're going to do the same thing for the elevation of this thing. Okay, so again, I took the wind from the left, and so you know that this is going to be some sort of, you know, trapezoidal piece that we had. Then you've got your 2 or 3 possible regions on the roof. Okay, and then on the leeward wall, you would have your constant pressure over here. And on this picture, this is where you would write your P values for the actual pressure in pounds per square foot. This will actually have numerical values. And then once you have that, then in the one of the coming videos, I'll show you how to apply those as forces to the building directly. But getting the pressure diagram is the goal here. The roof is a little bit different. Okay, it's again, it could be 3 regions, but remember we had H, 2H, and then greater than 2H is our distance, right? So for a small, you know, this is region 1, this is region 2, this is region 3. For a small roof, it's possible that maybe this guy isn't even on the roof anymore. And if that's not the case, then you could end up with just 2 regions, which I think this building will only have 2 regions on it. Okay, and that's fine. You just draw what it's capable of supporting, because I can't have wind out here somewhere pulling up because there's nothing for it to pull up on, right? So we just kind of, you draw all 3 to scale, and then whatever's on the building is what's on the building, is the way that we would start to kind of handle that. So anyway, that's the basis for how you start to compute wind pressures using the MWFRS method. I hope it's made a little bit of sense and kind of walked you through the process for analyzing and doing all of that. So anyway, if you toss us some comments down below if you got any questions, or otherwise, if the video was helpful at all, toss us a like, and again, be sure to subscribe to the channel. We greatly appreciate it. So with that being said, I will bid you all a wonderful afternoon. I'll see you all next time.